So, let us take a short recap of the development of the field of superconductivity. It was in 1908, let us just write as recap. So, 1908 the superconductivity is seen in writing in short for superconductivity as SC is seen in ultra clean mercury. And then on a large number of superconductors have been discovered, and they have been debated upon. Many experiments have been done, and it was around 1940, 3940 is the first phenomenological theory of superconductivity came up, which is called as the Ginzburg-Landau theory. And of course, after that 1957 was the celebrated BCS theory, which was the most successful microscopic theory that explained all the phenomena, all the experimental observations that are seen or that are made possible in the context of superconductivity. So, this is a BCS theory, and as we have seen that it is a non-perturbative theory, it is a variational theory, and it explains all the features of superconductor, conventional superconductor. What we mean by conventional will be made more clear later when we talk about unconventional superconductors. And then of course, lots of superconductors were discovered, including the organic superconductors, and it was only 1986 is when one has seen this development of the high temperature superconductivity. So, these classes of superconductors have been seen, which have TCs ranging from 40 Kelvin to about 200 Kelvin or even larger than that, and these are all copper oxide based superconductors. And then in early 2000 there were discovery of iron based superconductors and so on. So, various development that took place regarding the understanding of superconductivity, many of them were empirical, and to say how they are, let us see some of the results that were proposed and were found to be true, at least in certain superconductors. So, some of these empirical rules. So, it is found that compounds with on an average 5 to 7 electrons show larger TC. And examples are the ruthenium molybdenum, which has 5 electrons, rather 7 electrons, have 7 electrons. This show a TC of 10.6 Kelvin, whereas ruthenium, which has 8 electrons rather, show a TC of 0.5 Kelvin, while molybdenum, which has a TC which has 6 electrons, show a TC of 1 Kelvin. So, when a compound is made of ruthenium and molybdenum, which has on an average 7 electrons, which shows a TC which is about an order of magnitude higher. Okay. And then people wanted to understand the structural dependence. And when these studies of the structural dependencies were done, they found that there are structures such as A15 crystal structures, just tell you what that is, or which is also called as a beta tungsten structure, that has a higher TC, or all these structures have higher TCs. Let us see what a A15 or a beta tungsten looks like. Okay. So, this is typically a A15 crystal structure of A15 crystal structure of a compound called A3B, and so these are the A atoms are actually at this A atoms are these blank ones that are not filled, and the hatched ones are the B atoms. So, B atoms are actually at the body centered places of this, and if you form a line connecting the mid mid of these sides, and then you join them, and then they sit the A atoms sit at the at these symmetric positions, similarly at all the sides. So, all the sides will have these A atoms, 2 of them on each face, and they are and the B atoms are which are shown in the thatched lines are at the body centered places. Now, this has a larger TC. So, this called it is also called as beta tungsten structure. Okay. And this has a TC of about there are 2 compounds which were notable at that time. So, it was V3 Si, that is vanadium silicon, and niobium germanium. So, both these have this same structure A3B structure, where A is equal to V for the V3 Si and A equal to Nb for the Nb3Ge. So, this has a TC of about 17.1 Kelvin, and this has a TC of about Nb3Ge has a TC of about 23.2 Kelvin. And so, these are considered as high TCs, and in fact, a large amount of research really had stopped for TCs to be around 25 to 30 Kelvin, and it has rarely, in spite of all the efforts, it has rarely gone beyond that. In fact, even with the discovery of the organic superconductors, the TC only rose just by a few Kelvin, but it stayed pretty much around that till the discovery of the high TC superconductors. So, this 23.2 was a maximum for quite a few years. And it is proposed that with the electron phonon interaction, this is the maximum TC that one can have. As you understand that this temperature is very low, this temperature is nearly 250 degrees below the freezing point, and that is a freezing point of course, water that we are talking about. And so, for industrial applications or for any sort of applications related to making of superconducting wires, etc., this temperature is not a suitable one. If the temperature, the number that we show here are certainly not viable to achieve. However, this research continued, and these organic superconductors also were seen. Let me show you some organic superconductors. So, this is an organic superconductor. It is called as an intercalated. They are popularly known as intercalated graphite. So, these layers are what we know as graphene now. So, these are carbon atoms, the black dots are the carbon atoms which are arranged in the form of a honeycomb lattice. So, this is a side view being shown and this is the top view being shown, and then there are these two kinds of stackings that are usually taken when and now this graphene is actually a two sublattice, it has a two sublattice basis with A and B. So, if A is above A, if A sublattice carbon is above the A sublattice carbon in the successive layers, then it is called a AA stacking, and if A sublattice is above the B sublattice and it is only in the next layer or the next to next layer, again the A sublattices are aligned, this is called as a AB stacking. So, here potassium is intercalated between these layers of graphite, and you can see that these balls are these are the potassium which is represented by K. It's got a nice structure which is like a serpentine structure. So, these are the intercalated graphite, and this intercalated graphite actually showed superconducting below 1 Kelvin. So, this is organic superconductor. So, let us just write that these are organic superconductors. And Tc is about just about 1 Kelvin. So, it is a small transition temperature. However, there is another one, let us show that. This is called as K360. So, these huge buckyball structures or these fullerenes are occupying the body centered positions of a cube, and this has a larger Tc. Tc is about, so this is called K360 and the Tc is about 18 Kelvin. Okay. So, and by various using various organic compounds, the Tc could go all the way up to 30 to 35 Kelvin. I mean that is the maximum Tc that one could achieve with organic superconductors. These last two, the one that we have shown, this one the C8K and this K360 are called as the organic superconductors. That is pretty much the story of this conventional superconductivity, and many empirical these such laws were proposed, and most of them were found to be correct within a certain restricted sense. We will also see later that there is another this phenomenological or empirical plot that is presented, which is called as a Uemura plot in the context of when we come to the unconventional superconductivity. Right now, let us look at some experimental scenarios measuring the gap. Experiments measuring the energy gap of a superconductor. So, just to remind you that these superconductors have a certain Tc, which means that below that Tc, at any temperature below Tc, the superconductivity is robust. So, there is an energy gap that forms because of the formation of Cooper pairs. So, the Cooper pairs are bound state of two electrons of opposite spin and momentum, and which gives rise to the fact that there is a certain amount of energy that is required to break that pair, and that energy is supplied usually in the form of temperature, which is called as a thermal energy, or it could be in the form of magnetic energy, that is via a magnetic field. The most important thing about a superconductor is the measurement of its energy gap, so that we understand that how large is the gap, because this gap is actually a measure of the transition temperature Tc. In fact, it is found in the BCS theory that this gap is proportional to, so this gap is proportional to the KTc, and in fact there is a factor that is associated with it. In fact, the factor is that the more correct expression is that 2T is equal to about 3.5 KTc. So, you can see that the delta and KTc are of the same order. In fact, this number 3.5 actually ranges from 3 to 4.5 for most superconductors. So, the question is that how do we determine the gap so that we know what the Tc of that particular superconductor is, and a variety of things are measurement techniques are there. One of them is the absorption of electromagnetic radiation. I am writing in short for electromagnetic, it's EM radiation. So, the first question comes that what is the radiation frequency that we should use in order to measure the gap. For that, we should have an idea of what is the magnitude of the gap. This is, of course, we do not know a priori what is the magnitude of the gap, because that is what we are trying to find out, but at least we should have an idea so that we know what the frequency of the radiation is. And this gap delta is of the order of a 1 to 2 milli-electron volt. Now, how do we say it is 1 milli-electron volt, and your 1 electron volt, just for your knowledge, it is 11,000 nearly 12,000 Kelvin, it is 11,600 Kelvin. So, if it is a 1 MeV, then of course, it is about 10 to 12 Kelvin. So, that is the transition temperature that we were talking about. So, this gap must be of the order of a few milli-electron volt, maybe of the order of 1 milli-electron volt. So, if we want to use an electromagnetic radiation, the frequency should be this is that or let us just write it. So, it is by basically h nu has to match delta in order to break the Cooper pair. So, this is by delta over h, and this is equal to about if you use 1 milli-electron volt, it comes to around 2.4 into 10 to the power 11 hertz. So, it is basically in that regime, sorry, we write hertz like this. Okay. So, basically it is in this regime of 10 to the power 11 to 10 to the power 12 hertz, which are more than a gigahertz, and around 1920s and 30s, this kind of frequencies or rather electromagnetic radiation with this kind of frequencies were not available. It was only available probably in the early 50s, 1950s, where such things are possible, or rather they are achieved. And now, of course, we have even micrometer range electromagnetic radiation that are possible. So, let us see what how the experiments are done. So, in the experiment, a cavity is made in the superconducting specimen whose gap we want to measure. Then the EM radiation is guided into the cavity and allowed to undergo several reflections. Finally, the radiation is captured after it has undergone multiple reflection and hence absorption. So, what we actually see is the absorption intensity. So, this is that absorption intensity of this radiation. And what happens is that this absorption intensity of the radiation is actually plotted as a function of the frequency. But before that, what is plotted is actually IS. So, assuming that the specimen is in the superconducting regime and minus IN. So, this means that the superconductivity is destroyed while the experiment is carried on, keeping at the same temperature, but using a magnetic field. So, we know that magnetic field destroys superconductivity, giving rise to a normal state. So, that normal state intensity is also captured and divided by basically that is the normalization by the normalized intensity. So, basically you try to understand that there is a kind of a superconducting specimen and there is a small cavity being dug into it. The radiation, electromagnetic radiation of that 10 to the power 11 to 10 to the power 12 hertz frequency is guided into it. It undergoes a lot of reflection and finally, it has been captured by a detector, the absorption intensity. It is done for two cases. One is when the sample is superconducting and when the sample is normal, and the normal state is achieved by keeping the same experimental setup. However, and at the same temperature, but however using a magnetic field, the superconductivity is destroyed, giving rise to a normal state. And these are the intensities, the absorption intensities of this, the normalized absorption intensities of the superconducting and the normal state. And this is plotted as a function of nu. And so, this is say nu in units of maybe 10 into 10 to the power 11 hertz and so on. And then what is seen is that the plot is so this is around 5 and this is around maybe 10 and this is 0 and so on. So, this is that intensity, let us say it is in arbitrary units. Okay. So, what happens is that below a certain frequency, which is below 5 into 10 to the power 11 hertz, one actually gets the superconducting state has a larger absorption, and suddenly what happens is that this goes to 0 in the vicinity. So, there is an absorption edge, and in the vicinity of that 5 into 10 to the power 11 hertz, it goes to 0, probably a little more sharp, but this is what we show here. I mean, this could be a little sharp depending on the material. So, basically what it means is that beyond these 5 into 10 to the power 11 hertz, this frequency, there is no difference between the superconducting state absorption and the normal state absorption. Now, the question is that why does it happen? And of course, if you go to larger frequencies, the difference between them remains as 0. And so, this abrupt drop of this absorption spectrum results from the quantum this theory of, or rather the quantum energy of the radiation is breaking, or it is becoming equal to the binding energy of the pair, or the energy gap that we talk about, and then the pairs, the Cooper pairs are dissociated. To summarize this plot, beyond a certain frequency, which is here that 5 into 10 to the power 11 hertz frequency, the absorption in superconducting state and normal state vanishes, which means that there is no distinction between the superconducting state and the normal state, which means that it is basically the superconductivity is gone. So, that tells you that there is this frequency which is equal to the gap, and by the gap can be estimated for this kind of from this kind of experiments. It is notable to mention that similar absorption edges are also seen in semiconductors. However, the gap in semiconductors is typically 3 orders of magnitude more, or 10,000 or rather 1,000 times more than that of the superconducting gap. And in silicon it is about 1.1 electron volt, in germanium it is about 0.8 electron volt, and hence the frequencies or rather the absorption edges are seen at much smaller frequencies, because the energy gap being larger. So, basically this conclusively tells us that the magnitude of the gap can be determined from this absorption of the electromagnetic radiation. Let us see one more experiment that shows also that measures gap. Before that, let us also sort of write down the magnitude of the gap. So, this is the experimental data. So, for NB3SN, which is again A15 crystal structure, which is called as the beta tungsten structure, the Tc is about 18 Kelvin. So, Tc in Kelvin, and this 2 delta in MeV. I just there is no particular reason that 2 delta is used, but since the 2 delta has a value, that is called as a magnitude of the gap. Delta is in this conventionally, because the Fermi energy is actually placed at the middle. So, there is a gap minus delta to plus delta. So, the magnitude of the gap is 2 delta. So, this is about 6.55 milli electron volt. This is a fairly newer superconductor, boride superconductor, is called magnesium boride. It has 40 Kelvin, and this has MeV 2 delta equal to 10 MeV. RB3C60, these are these organic superconductors, intercalated organic superconductors, which has a 30 Kelvin, and the gap is about 12 MeV, and there is a erbium rhodesium boron, that is a 9 Kelvin, and this is equal to 3 Kelvin. So, as you see that there is a nice correlation, or rather 2 delta is actually very closely correlates with Tc. So, once you have a magnitude of the gap available to you through experiments, Tc is or at least an estimation of the Tc is also available. Let us see one more experiment here, which is called as the ultrasonic attenuation. So, basically there are these sound waves are nothing but the lattice excitations or phonons. So, these sound waves actually interact with the conduction electrons. So, this is called as the electron phonon coupling, and these so if one sends a sound wave through a superconducting specimen. So, it could happen that there are still below Tc there are some unpaired electrons, conduction electrons available, and they would absorb the radiation, and the absorption intensity of this ultrasound can be measured. And what it shows is that it shows a plot like this. Shows a plot like this. So, this is T versus Tc, and so this is equal to 1. So, let us write it. So, this is equal to 1, and this is the absorption intensity. Okay. So, one gets a plot like this. What it means is the following, that below Tc, so this left side is between 0 and 1, we have a superconductor, and this is a normal. So, in superconductor there are very few unpaired electrons, they are all mostly they are Cooper pairs, which are which form the the constituents of the superconducting state. And that is why the superconducting state has a gap. Say there are few unpaired electrons, those will absorb the sound, and this, as you go deeper into the superconducting regime, by reducing the temperature, the number of such unpaired electrons go down drastically, and so the ultrasound attenuation also will go down drastically, going to 0, and so the absorption intensity will go to 0, which means that through a superconducting specimen, if the ultrasound is sent or the sound waves are sent, they will propagate without any significant absorption. One would get the same intensity of sound at as one would have gotten as the incident sound. So, this gives the idea of the Tc. This is plotted of course T by Tc, but in actual experiments one does not know what is Tc. So, it is plotted as a function of T, and the Tc can be extracted from this, and the Tc, as I said a number of times, Tc is a measure of the gap. So, the gap can be determined. Since so Tc can be determined, hence the energy gap determined. Okay. So, this is the ultrasound attenuation, and then there are also some tunneling experiments. So, what happens is that if an electron, so make a junction of N and S, and this is the, and we are connecting a battery voltage. So, an electron can actually be made to appear at the junction. Now, this the electron will not pass through, because the electron will see it as a barrier, as the superconducting state is say fully paired, which offers an energy gap which is equal to the delta. So, if this electron does not have this, then there is no current, and that is what is seen in actually this experiment. So, this is that the current or the conductance, and so it shows that it is like this. Okay. So, this is as a function of the voltage, the biasing voltage. So, this Vc is equal to like delta 0 over E, and this is of course at T equal to 0 or very low temperature, and at T less than Tc this. So, this is T less than Tc not equal to 0. So, one has a form which is that. So, it is a smooth curve. Let me just draw it once more. So, that is the properties of this junctions, that it does not allow flowing of the current, and one gets this the tunneling current versus the voltage. So, it is the IV characteristics for these NS junction, and one finds that it happens, it starts taking off, the current starts taking off only at Vc, the critical voltage, which is equal to delta 0 by E. So, just by noting Vc in an experimental setup, one could find out what is delta 0. But it seems like the thing is not that straightforward. There are additional things that are happening which are called as the Andreev reflection. And let us quickly go through what is Andreev reflection. So, in experiments, I mean this is also an experimental setup, but in other experiments the electron suffers two reflections. One of them is called as a normal reflection, and the second is called as the Andreev reflection. So, the normal reflection is just the same as what one sees here, that the electron, when it does not have the energy to overcome the barrier that is that exists in the superconducting side, it will simply turn back, giving rise to a normal reflection. And there is something called as the Andreev reflection. So, what happens is that at the normal superconductor interface, so let us explain Andreev reflection. So, an electron incidents at the interface of the normal superconductor, we will simply write as NS junction. So, then what happens is that the Cooper pair is injected into the superconductor region, which is the lead. So, it is that a picture that we had shown. So, and then the incident electron is annihilated third, importantly, because there is a generation of a Cooper pair, a hole retraces the path of the incident electron So, one A energy is conserved in the process, we will show that, and momentum is almost conserved. will tell you what we mean by almost conserved. Okay. So, basically what happens is the following at this boundary. So, this is the NS boundary. So, this is N and S. So, there is an electron that goes, okay. A hole comes back, okay, and a Cooper pair that transmits here with charge 2e. Okay. So, this is an electron and a hole. Let me draw it better. Okay. So, this is that Cooper pair, and since Cooper pairs can travel inside a superconductor, so that would travel, and this electron gets annihilated and there is a hole. So, this electron has spin up and the hole has spin down, and basically this can give rise to low energy tunneling current. So, at very low energy you do not need to actually cross the gap, you still can have tunneling current even at 0 bias, that is very low energies. So, this is known as Andreev reflection. So, the how is momentum and energy conserved? So, k electron equal to kf plus epsilon by h cross Vf, and k hole it is equal to kf minus epsilon by h cross Vf. They have opposite direction, opposite motion, and which appears from the groove velocity. So, 1 by h cross del E del k is actually negative, as you can see from these expressions. So, the groove velocity is oppositely directed. Then of course, energy is conserved. So, Cooper pair has energy 2 EF, that is the minimum energy. So, these things, the Cooper pairs are formed at EF. So, the incident electron has energy epsilon f plus epsilon, and the reflected hole has energy which is epsilon f minus epsilon. So, if you add both of them, it becomes 2 epsilon f, and the momentum, so let us do it here, momentum is conserved up to k electron minus k hole. This should be less than 1 over xi, or if you want, if it is h cross and h cross here. So, it is up to this, where xi is the coherence length, which is equal to h cross Vf by pi delta 0. So, in this process 2e charge is transferred from N to S. Okay. Let us just show it graphically. So, it is this is the E versus K, this is the, so this is your N and this is the S. So, this gap is delta. Okay. So, there is a Cooper pair that is of 2e, that goes from here. So, there is this K. So, there is a hole here which moves in this direction. There is an electron here which moves in this direction. Should have drawn at the same. So, this is that electron, this is that hole. So, this is the momentum of the hole, this is the momentum of the electron, and so somewhere in between this Kf. So, this is the superconducting state. So, this is normal N and this is S, and so that is the so basically the structure. So, there is a Cooper pair that propagates and so on. So, this is called as Andreev reflection, and to see that we have current at almost 0. So, this is the Andreev reflection. So, basically you see that below delta there is a current which is pretty large, and then of course at delta the current after beyond delta the current goes down for a reason that also can be explained simply. So, this is the feature of this Andreev reflection, and it is there, it is present in all normal superconductor junctions, or even if one actually introduces a barrier between the normal and superconducting junction. Just to say that the normal is usually a metal such as aluminum, etc., and the sometimes the insulating barrier being introduced between the normal and the superconducting junction. One can do the same experiment. There are additional features which we do not want to go into here. Neither we want to go into the detailed derivation of these tunneling current, but that is quite possible. It requires one to understand the Bogoliubov-Dijen formalism in order to handle the superconducting properties. And so, there are so this insulating layer in between is formed by what is known as alumina Al2O3, the aluminum oxide, which is usually a very good insulator, and not only that, it can be very nicely formed as an interfacial regime with a desired thickness for a given experimental setup. So, these are some of these experiments. So, this edge would determine that there is a the delta is there, and if I take a differential conductance, then it will show that there is a peak there. Okay. So, this is I versus V, whereas the di dV versus V would show a peak, and so where there is a like a discontinuity, and so this will be the position of delta or the energy gap. So, these are some of the experiments. This list is of course not exhaustive. There are many other experiments, but one needs to understand at least a few how experimentally one determines the gap.